So,
I have a question.
yeah, go ahead.
Can you go back to the part where it says square matrix?
Mhm.
Thank you.
A square matrix is a matrix that has the same number of rows as columns. So like a 2 by 2 matrix is a square matrix, a 3 by 3, 4 by 4, 5 by 5, 6 by 6. These are all square matrices because they have the same number of rows and columns. Okay. And square matrices become important a little later on in this chapter when we start finding the inverse of a matrix and solving systems by using what's called matrix inversion. All right, let me know when you're ready to move on.
I'm ready.
Okay. Okie dokie. Suppose I have a system of 3 linear equations and 3 unknowns. So this is a linear system of 3 equations and 3 unknowns. Of course, it's a linear system because all the variables are raised to the first power. We can represent this system using a matrix, specifically using a 3 by 4 augmented matrix. 3 by 4 augmented matrix. All we put in this matrix are just the coefficients of the left-hand side equations and the right-hand side constants. So 3, 2. Now there is no z variable for the first equation, so we say 0, a vertical line, and we put a 5. That's how we enter the first equation into the matrix. Second equation, just the coefficients. 1, -1, 3, and 1. Second equation, just the coefficients and the right-hand side constants. Okay. So there you go. We have represented the system of 3 linear equations and 3 unknowns using a 3 by 4 augmented matrix. Most textbooks have a solid vertical line. Some textbooks have a dashed vertical line. This line basically separates the left-hand side coefficients of the system from the right-hand side constants of the equation. This is kind of like the x column, the y column, and the z column. Okay, so notice you would have the first equation as being 3x plus 2y plus 0z equals 5. This vertical bar means the equal sign. Second equation, 1x minus 1y plus 3z equals 1. Third equation, 2x plus 1y plus 1z equals 4. Okay. Any questions how I represented that system using a 3 by 4 augmented matrix? All right. So, ladies and gentlemen, what are we going to do? Once we represent a system using a matrix, how are we going to solve the system? Well, ultimately, we're going to have to get this matrix into a special form called echelon or reduced row echelon form. And what does it mean for a matrix to be in row echelon or reduced row echelon form? Well, we're going to show you that in a moment. But how can we, manipulate a matrix algebraically and still maintain an equivalent matrix? Well, there are 3 elementary row operations that we can subject a matrix to. They're called elementary row operations. There's 3 of them, all right? And I'm going to go to our textbook and we're going to take a look at them. All right. Now, if I have a system of 3 equations and 3 unknowns, ladies and gentlemen, do you think it would be legal to just interchange any 2 equations in the system and still have the same equivalent system? In other words, do you agree that I could maybe let the second equation be up here as the first equation and the first equation be the second equation? Do you think that would change the system if I just flip the equations around? If I just interchange any 2 equations? Do you think it would still be the equivalent system, same solution?
Yeah.
That seems like a harmless move. Do you agree? It doesn't matter which equation you call first, second, and third. That's totally immaterial. All right, so that basically provides the foundation for the first elementary valid row operation. We can always interchange any 2 equations. And so, ladies and gentlemen, with any matrix, we can always interchange any 2 rows. And when you do so, you'll still have an equivalent matrix. because it's analogous to interchanging two equations in a system of equations, still the same system of equations. So here's a 2x3 augmented matrix. They've interchanged rows 1 and 2. Easy thing to do, okay? But this matrix over here is still equivalent to the original matrix. Another thing you can do is you can always multiply any equation in a system by a non-zero constant. You will still have an equivalent equation, hence you will still have an equivalent system. And any solution to the equivalent system will still be a solution to the original system. This provides the second elementary row operations that is legal to subject a matrix to. I can always multiply any row of a matrix by a non-zero constant. So this notation here is saying that I took row 1 of this matrix on the left and multiplied it by 3 to form a new row 1. So every entry in row 1 got multiplied by 3 to give us a new equivalent row 1. That's a valid elementary row operation. This matrix over here is still equivalent to the original matrix over here on the left. There's another thing I could do. I could always multiply one equation by a non-zero constant and then add it to another equation to form another equation, and I would still have an equivalent system. So the third valid elementary row operation is that I can always take any row of a matrix, multiply it by a non-zero constant, and then add it to another row to form a new row. This is saying that in this matrix over here to the left, that row 1 is going to be multiplied by 3, then added to the corresponding entries in row 2 to form a new row 2. Notice row 1 is not changing here. Row 2 is changing, but we're using row 1 to change row 2. So every entry in row 1 got multiplied by 3 and then added to row 2. So what's 3 times row 1? It would give you 3, 6, and 15. And when you add it to the corresponding entries in row 2, you form a new row 2, 0, 1, 2. Do we understand these 3 elementary row operations? So this matrix over here is still equivalent to this one over here. 3 valid elementary row operations, ladies and gentlemen. You can always interchange any 2 rows of a matrix. You can always multiply any row by a non-zero constant. And you can always add a multiple of one row to another row in a matrix. Any questions about these elementary row operations? All right, so these are three valid or legal moves we can subject a matrix to and still preserve an equivalent matrix. Okay. All right, let's go to example. Let's see something here. Let's go to example 2. This is in section 6.1 in your textbook. So the examples are right here. So if you miss anything, you're welcome to, study these examples over in your textbook. Here is a 3x4 augmented matrix, ladies and gentlemen, and it would pertain to a system of 3 linear equations and 3 unknowns. What would the first row? What equation would come from the first row? Anybody want to read off the equation that would be represented by the first row in this matrix? What would be the first equation?
Would it be 4x plus 3y equals 5?
That's right. 4x plus 3y equals 5. Notice there's no z variable in the first equation. The second row would generate which equation? 1x plus 4y minus 1z equals 9. The third row would generate the third equation in the system, namely 2x minus 3z equals -8. All right, elementary row operation number 1 they want to subject this matrix to is nothing more than just interchanging rows 1 and 2. And so you can see them do that down here. Notice rows 1 and 2 just get interchanged, and we still have an equivalent matrix over here to the right. That's a valid elementary row operation, which does not change your matrix. This matrix still here over here is still equivalent to the original one. Elementary row operation number 2 is they took the matrix and multiplied the first row by 1/4 to form a new first row. So every entry in row 1 got multiplied by 1/4. So 4 times 1/4 gives you the new 1/1 entry as being 1. 3 times 1/4 gives a new 1/2 entry as being 3/4. 0 times 1/4 keeps the 1, 3 entry as a 0. And 5 times 1/4 nets us with the 1, 4 entry being updated to 5 fourths. Nonetheless, this matrix on the right is equivalent to the original matrix over here. Third elementary row operation is saying that we're going to take row 2 of this matrix, multiply it by -2, and then add it to row 3 to form a new row 3. Notice we're not changing row 2, we're using row 2 to change row 3 in an equivalent way. So what they did first here is they took row 2 of this matrix and multiplied every entry by -2. So 1, 4, -1, 9 becomes -2, -8, 2, -18. They then add those entries to the corresponding entries of row 3 to form a new equivalent row 3 of 0, -8, -1, -26. And ladies and gentlemen, we have an equivalent matrix over here to the right. This matrix is equivalent to the original matrix. Any questions on example 2 with those elementary row operations that are subjected to this matrix here? Is this making sense here? So,
I have a question.
yeah.
So the gist of this is performing the row operations to get equivalent matrix to the first one that we did the row operation on.
Yeah, I mean, when you perform an elementary row operation on a matrix, the resultant matrix will still be equivalent to the original one, okay? Now, I have not shown you, where we're ultimately going with these systems and what form we have to get our matrix down into in order to solve the system. But I'm just warming you up to these elementary row operations that are legal to subject the matrix to. Is that making sense, these 3 elementary row operations?
Yep.
Okay, so that's all we're doing so far. We're just warming up to these 3 different elementary row operations, which are valid moves when it comes to a matrix and manipulating the rows of a matrix in order to obtain a equivalent resultant matrix. All right. Okay, so done with that. Okay, now, ladies and gentlemen, I need to go over on page 566 in the purple box something very important. This is on page 566 in your textbook. This purple box entitled Row Echelon Form and Reduced Row Echelon Form. All right, these are special forms for a matrix that we're ultimately going to be aiming towards in solving these systems using matrices. We say, ladies and gentlemen, that a matrix is in row echelon form if it satisfies the following conditions. Number 1, any rows consisting entirely of zeros will always appear at the bottom of the matrix. Number 2, for all other rows, the first non-zero entry you will run into from left to right, if you move from left to right in any row of a matrix, the first non-zero entry you have to run into has to be a 1. This is called the leading 1 of the row. Number 3, the leading 1 in each non-zero row is always to the right of the leading 1 in the row immediately above, or the row that precedes the row. Now, this is about as clear as mud in your mind, but with examples, you'll start to understand what row echelon form is for a matrix. We say that a matrix is in reduced row echelon form if it is not only in echelon form, namely that it shares all these characteristics, but there's also one other requirement. The added requirement is that each row with a leading entry of 1 has zeros above the leading 1, okay? All right, so ladies and gentlemen, let me show you some matrices that are in row echelon form. Row echelon form. And we normally abbreviate row echelon form as REF, row echelon form. All right, this matrix here, this 2 by 3 matrix would be in row echelon form by definition. This matrix is in row echelon form, okay? Number 1, there's no row with all zeros, so we don't have to, have it appear at the bottom because there is no row consisting of entirely zeros. Number 2, as we progress in each row from left to right, the first non-zero entry we run into is a 1. progress from left to right in the first row, we run into a 1. From left to right in the second row, the first non-zero entry we run into is a 1. The third requirement is that the leading one that occurs in row 2 has to be in a column that is to the right of the column that contains the leading one in the previous row, namely row 1. So in other words, this leading one in row 2 is to the right of the leading one in row 1. We say this matrix is in row echelon form. Everybody see that there? Furthermore, ladies and gentlemen, we call the entries of a matrix the 1-1 entry, the 2-2 entry, the 3-3 entry, ... the NN entry, depending on, you know, whatever, how many rows and columns you have in your matrix. We call these entries the main diagonal entries of a matrix, called the main diagonal entries, or the main diagonal elements of a matrix. Okay, so the 1-1 and the 2-2 entries or elements of this matrix, notice, are all 1s. And that is also going to be a characteristic of a matrix to be in row echelon form, is that on the main diagonal you must have either all 1s or a 0 on the main diagonal. All right. This is an example of a 2x3 matrix that's in row echelon form. Here's an example of a 3x4 matrix that is in row echelon form. Ladies and gentlemen, we say that this 3x4 augmented matrix is in row echelon form. Notice we don't have any row that consists of all 0s, because if we did, it would have to appear at the very bottom of the matrix. But notice the first non-zero entry we run into in each row from left to right is always a 1. Leading 1, leading 1, leading 1. And notice that the leading 1 in any subsequent row is always to the right of the leading 1 of the previous row. This 1 is in the column that's to the right of the column that contains this 1. This 1 is in the column to the right of the column that contains this 1, which is in a column to the right of the column that contains this 1. We say this is in row echelon form. What are you also noticing about the entries on the main diagonal? The entries are always what? 1s, right? This is called the main diagonal here. The 1-1 entry, the 2-2 entry, the 3-3 entry. What do you notice about the entries below the main diagonal? What's your observation? When a matrix is in row echelon form, the entries below the main diagonal are always what?
0.
Zeros. Notice, always 0s below the main diagonal. Notice that's also a characteristic of row echelon form, although it was not stated explicitly in that definition. That's also a characteristic. Okay, so these matrices are in row echelon form when they're in that form. Let me show you another example of a matrix that's in row echelon form. This one is in row echelon form. All right, this is in row echelon form. Notice we do have a row that contains nothing but 0s, and if we do have such a row, it must occur always at the very bottom of the matrix. And notice the non-zero leading entries of any row from left to right. The first non-zero leading entry is always a 1. And so this is said to be in row echelon form also. Okay. All right. Is this matrix here in row echelon form? Is this matrix in row echelon form? That one there?
No.
Why not?
Didn't it say that the leading one has to be to the right of the one above it?
Yeah. Notice this leading 1 of row 3 is in a column that's not to the right of the the column that contains the leading 1 of the previous row, the second row. this one is to the left of this one. It should be to the right. It should have to be over here, correct? This is not in row echelon form. All right. Okay, so any questions? Do we understand what row echelon form is for a matrix? There is, ladies and gentlemen, a more restrictive form for a matrix called reduced row echelon form. And as you would guess, it's nice to abbreviate this as RREF, reduced row echelon form. These matrices are in reduced row echelon form. This matrix is said to be in reduced row echelon form. You see that? Where we have ones on the main diagonal and we have zeros below and above the main diagonal. And notice this one is in the column to the right of the column that contains the one in the previous row. This is called row reduced echelon form. Here's another matrix that's in a row echelon reduced form. This matrix is said to be in row reduced echelon form. One's on the main diagonal, and notice all the other entries below and above the main diagonal are zeros. That's what it means to be in row reduced, or excuse me, reduced row echelon form. Okay, so that's in reduced row echelon form. This matrix here is in reduced row echelon form. Hold on a second here. All right, so this matrix is in reduced row echelon form, where we have ones on the main diagonal, but we do have a row that consists of all zeros, but it does occur at the very bottom, and that's where it should be. Wait a minute, there's one other instance. I'm sorry, that this is now in reduced row echelon form. That has to be a zero there. You have to have zeros below the main diagonal and above the main diagonal, because that's reduced row echelon form. Okay. All right. So why is this matrix here not in reduced row echelon form? Why is this not in reduced row echelon form? This is not reduced row echelon form.
There's the 7 up in the top right.
That's right. All the entries above and below the main diagonal have to be 0. This is causing this to not be in reduced row echelon form. Okay. All right. So now that we have an idea as to what it means for a matrix to be in row echelon versus reduced row echelon form, ladies and gentlemen, we can begin to solve these systems of equations using matrices. Okay. Any questions about any of this? Reduced row echelon form versus row echelon form. All right, there's two techniques that is being illustrated in this section as to how we're going to solve systems of linear equations using matrices. The first technique is called Gaussian elimination. It's called Gaussian elimination in honor of Carl Gauss, who was a prominent mathematician, a German mathematician. Ladies and gentlemen, you can look up Carl Gauss's biography. Many contributions to the field of mathematics came from this genius by the name of Carl Gauss. Okay, Gaussian elimination requires our augmented matrix that basically represents our system of equations, our augmented matrix, be put into row echelon form. So for Gaussian elimination enabled us to solve a system of linear equations, our augmented matrix, which contains the system or represents the system, has to be put into what's called row echelon form. by using, and how do we do that? How do we get it into row echelon form? We use elementary row operations. By using elementary row operations, that's how we achieve that. Okay. And then, ladies and gentlemen, a more restrictive technique, a more strenuous technique is called the Gauss-Jordan elimination method. Gauss-Jordan elimination is similar to Gaussian elimination, but there's one other requirement here. Gauss-Jordan elimination requires our augmented matrix, which represents our system of equations, be put into not just row echelon form, but reduced row echelon form by using elementary row operations to accomplish that. Okay. Row operations. Now, Gaussian elimination is a little bit easier. It's one less step, if you will, or a couple less steps than Gauss-Jordan elimination. To get a matrix into row echelon form is a lot easier than to get it into reduced row echelon form. The trade-off is once you get your system into reduced row echelon form, you can just read off the X, Y, Z coordinates of the, or just the X, Y coordinates of the ordered pair solution of the system. With Gaussian elimination, you have to back substitute to recover the coordinates of your ordered pair or ordered triple solution, whatever the case might be, if you're solving a system of 2 or 3 linear equations and 3 unknowns. Okay. All right. Now, so the first method I'm going to show you, ladies and gentlemen, I'm going to show you how to solve a system of 2 linear equations and 2 unknowns by using Gaussian elimination. To do that, this is the step procedure we go through. There's steps. So how do you solve a system of 2 linear equations and 2 unknowns using Gaussian elimination and elementary row operations? Well, step number 1 is we need to make the 1-1 entry of a matrix become a 1. That's step number 1. We have to force a 1 in the 1-1 entry. The row 1, column 1 entry must become a 1. If it's not, we have to use an elementary row operation to make it 1. Number 2, the second step is once we make the 1-1 entry a 1, we are going to use row 1 then to make all the entries below the 1-1 entry in column 1 become all zeros. So once we make the 1-1 entry become a 1, we're going to have to clear out the rest of column 1. I like to say clear out the rest of column 1 below the 1-1 entry. We have to make all the entries in column 1 below the 1-1 entry become zeros. And to do that, we have to use an elementary row operation. Number 3, once we do that, we then make the 2-2 entry become a 1. And we do that by performing an elementary row operation on row 2. Once the 2-2 entry is a 1, we then have to use row 2 to make all entries below the 2-2 entry in column 2 become all zeros. In other words, we use row 2 to clear out the rest of column 2 below the main diagonal. Last step, once we do all this, steps 1 through 4, our matrix will be in row echelon form. So our matrix, after performing steps 1 through 4, will be in row echelon form. And then, ladies and gentlemen, we cover our ordered pair solution or ordered triple solution, regardless of whether we're solving a 2x2 system or a 3x3. We have to use back substitution to recover the X, Y, and or Z coordinates of the solution. All right, that's about as clear as mud in your mind, but those are the steps. You might want to at least document those by taking a picture of those or maybe writing those down. I'm going to give you a couple minutes or a minute or so to do that. Please do account for all those steps, as it provides a roadmap as to how we are to perform Gaussian elimination on a matrix to solve a system of equations. Because this is not in your book right here. These steps are not laid out in your textbook. And the nice thing is that this is a recording, so, oh gosh. You know, I still have to post a recording from 2 days ago. Yeah, I will do that after the session, that recording, this recording. All right. All right. So these are the steps that we're going to kind of follow in solving a system of two linear equations and two unknowns using Gaussian elimination. All right, here we go. We're going to look at one now. So solve by Gaussian elimination. And here is our system. 2x plus 3y equals negative 13. 1x plus 4y equals negative 14. All right, the first step is we need to represent this system of two linear equations, two unknowns, by using an augmented matrix. So here we go. The first equation will be entered in as 2, 3, vertical line, negative 13. Second equation is entered in as 1, 4, vertical line, negative 14. That's how we represent our system in a 2 by 3 matrix. 2 rows by 3 columns. Okay, this is a 2 by 3 matrix. And now, ladies and gentlemen, we're going to have to get this matrix into to the left of the vertical line. We want to get it into row echelon form. So how do we do that? First, we have to make the 1, 1 entry become a 1. What elementary row operation could I subject this matrix to achieve that? Anybody got an idea? How can I make this 1, 1 entry become a 1?
Swap the two equations, flip them over.
Yeah, let's just interchange rows 1 and 2. Do you agree? And then the 1, 1 entry will be a 1. How easy is that? So therefore, let's interchange rows 1 and 2. This notation is saying that. We're going to interchange rows 1 and 2. And our new equivalent matrix then is going to be 1, 4, vertical line, negative 14. And the second row becomes 2, 3, and negative 13. Good. So the 1, 1 entry now is a 1. The 1, 1 entry is a 1. Now, the second step, we're going to use row 1 to clear out the rest of column 1. In other words, we're going to use row 1 in a valid elementary row operation to make the 2, 1 entry down here become a 0. We want to clear out the rest of column 1 below the main diagonal, which is the main diagonal element is 1, 1 here. What do I have to add to 2 to make it 0?
Negative 2.
And where am I going to get that negative 2 from? Well, there's one valid elementary row operation says I can always multiply a row of a matrix by a non-zero constant and add it to another row. So what I'm going to do is I'm going to multiply row 1 by negative 2, add it to the corresponding entries of row 2 to form a new row 2. Symbolically, what did I just say? This is what I just said. I'm going to multiply row 1 by negative 2, add it to row 2 to form a new row 2. Notice I'm not changing row 1. I'm using row 1 to change row 2 in an equivalent way. So therefore, let's do this here. I'm going to have to take negative 2 times row 1. Row 1 is 1, 4, vertical line, and negative 14. I'm going to add to that row 2, which is 2, 3, vertical line, and negative 13 to form a new row 2. What's negative 2 times 1? That gives me negative 2. And what's negative 2 plus 2? 0. So my new 2, 1 entry becomes a 0. What's negative 2 times 4? Negative 8. What's negative 8 plus 3? Be negative 5. What's negative 2 times negative 14? It's positive 28. Positive 28 plus a negative 13 turns us into a what? of 15, and this is my new row 2. Let's pencil in my new row 2. Notice I did not change row 1 this time around. I used row 1 to create a new equivalent row 2, namely 0, -5, 15. Everybody understand how we got to this matrix so far? All right, now the rest of column 1 has been cleared out. What's the next move now? The next move now is to make the 2-2 entry become a 1. What do I have to multiply row 2 by to make this a positive 1? What are you going to multiply -5 by to make it 1? Now, some of you are saying, couldn't I add something to row 2 to make this 1? Well, if you do that, be careful, because if you add a multiple of row 1 to row 2 to make this become a 1, guess what? This entry is going to go from being 0 to a non-zero entry. We will have destroyed our work in clearing out the rest of column 1 back over here. So don't do that. No, we just got to multiply row 2 by what? What do I multiply -5 by to make it 1?
-1/5.
-1/5.
-1/5. So here's what we're going to do. I'm going to take row 2 and multiply it by -1/5 to form a new row 2, a new equivalent row 2. That's a valid elementary row operation. You can always multiply any row by a non-zero constant. Okay. So we're going to take -1/5. We're going to multiply it by row 2, which is to say by 0, -5 rather, and 15. And by doing that, we're going to form a new equivalent row 2. -1/5 times 0 keeps the 2-1 entry as a 0, which it must be. -1/5 times the 2-2 entry, -5 turns the 2-2 entry into a positive 1. That's what we want. And -1/5 times 15 turns the 2-3 entry into what? What is -1/5 times 15? That gives you -15/5, which is what? -3? -3. So therefore, this entry becomes a -3. There's your new equivalent row 2. Let's pencil that in. So my new equivalent matrix now looks like this. Notice we did not change row 1. Row 2 is 0, 1, -3. All right, ladies and gentlemen, what have we accomplished? We started with our 2x3 augmented matrix that represented our system of 2 linear equations, 2 unknowns, performed elementary row operations, and got it into what form? What form is this matrix in? Anybody? What form is this? That's called row echelon form. Everybody see that there? Now, all we have to do to recover our ordered pair solutions coordinates is to use back substitution. The first row gives me what equation? What equation comes from the first row? This is like your X column, your Y column, and your right-hand side constant. So the first row generates the equation 1x plus 4y equal to -14. That's the first row. That's the first equation. Second row generates the second equation, which is to say 0x plus 1y. So we got 1y equals -3. Guess what? We have the y coordinate of our ordered pair solution. It's -3. That's what y is. To find x, we're going to have to take the -3 and back substitute it up into the first equation and for y. And then we'll solve for x. Hence, when we do that, our first equation becomes x plus 4 times -3 equals -14. And now we just solve for x. So we got x minus 12 equals -14. Add 12 to both sides. X walks out of this with a value of -2. And ladies and gentlemen, we are done. Our ordered pair solution to this system is going to be the ordered pair -2, comma, what? -3? That's it. Does that make sense? How we solve this system of 2 linear equations and 2 unknowns using what's called Gaussian elimination, which has us taking the system in the form of a matrix, subjecting the matrix to valid elementary row operations in a particular order to get the matrix looking ultimately like row echelon form. And then once we got row echelon form, then we can recover the coordinates of our solution. Any questions about that, ladies and gentlemen? I know it seems somewhat tedious, but it is a method that I need to expose you to in college algebra. It's called Gaussian elimination. Now that was just for a system of two equations and two unknowns. Could you imagine that it would get a little more lengthy for a system of three equations in three unknowns? And could you imagine trying to solve a system of 10 equations and 10 unknowns using this technique? That would take a while. That would take a long while, in fact. All right, that's where we turn it over to computers when the systems become massive and large. Your weather forecast every day of the things you're interested in, like the high temperature, maybe the wind speed, the dew point temperature, all those things are generated by having supercomputers solve massive systems of millions of linear equations and billions of unknowns. These computers that crank out 20 trillion calculations per second still require about 30 minutes of nonstop crunch time to generate a 2-day forecast for the Northern Hemisphere. 30 minutes of nonstop crunch time cranking out 20 trillion calculations per second. That shows you the size of numerical weather prediction, how the scope of that problem there. Okay. All right. Okay, let's see here. So my Gaussian elimination. All right. Everybody understand that there? Okay, how we did Gaussian elimination on that system of two linear equations, two unknowns. All right, well, I will show you how to solve this system by Gauss-Jordan elimination. Now, with Gauss-Jordan elimination, we have to add another step. So, ladies and gentlemen, how would I solve a system of two linear equations and two unknowns using not Gaussian elimination, but by using what is called Gauss-Jordan elimination? Well, what we'd have to do here is we would have to add another step into the process here. So to solve a system using Gauss-Jordan elimination is we would get rid of the step that has back substitution. We don't need that step anymore, but we would have to add another step on here. All right, step number 5 then, using Gauss-Jordan elimination, would be all these steps in this order up to this step. Then we'd have to add another step. And the other step would then be saying, once I use row 2 to make the entries below the 2 entry in column 2 become 0, I have to also then use row 2 to make all entries above the 2 entry in column 2. All zeros. Okay, so there is one added step in here. So this would be the procedure for solving a system of two linear equations, two unknowns using Gauss-Jordan elimination. These steps coupled with this step now. All right, and then the last step is then we can just read off. So the payoff is handsome once you get it into reduced row echelon form. Then we just have to read off the coordinates of our solution from the matrix. It's that simple. Okay. So I'm going to illustrate how to solve a system of two linear equations, two unknowns using Gauss-Jordan elimination, which has these added little steps here. Okay. All right. So let's see here. So let's give us a system to play around with here. All right, here we go. Let's use this one here, negative 3x plus 11y equals 58. And then x minus 3y equals negative 16. First step is to represent this system using a 3x4 augmented matrix. So here we go. Equation 1 goes in as -3, +11, vertical line, and then 58. Second equation goes in as 1, -3, -16. Step number 1 is we want to make the 1, 1 entry become a 1. How can we achieve that? Just interchange what? Rows 1 and 2. That's all we got to do. So let's interchange rows 1 and 2. My equivalent matrix will be 1, -3, -16, and then -3, 11, and 58. Good. Next move, ladies and gentlemen, is I got to make use row 1 now to clear out the rest of column 1. I got to make this 2, 1 entry become a 0. To do that, I have to add 3 to -3. Where am I going to get that from? Well, I'm going to take 3 times row 1, add it to row 2 to form a new row 2. That's what I'm going to have to do. Okay. So I'm going to take 3 times row 1, which is this. Add that to row 2 to form a new row 2. 3 times 1 is 3. 3 plus -3 is 0. 3 times a -3 is -9. -9 plus 11 is 2. 3 times -16 is -48. -48 added to +58 is a +10. There's your new equivalent row 2. Let's pencil that in. That's your new equivalent row 2. So my matrix now has been transformed into an equivalent matrix that now looks like this. Okay, got a matrix down to this. We're shooting for reduced row echelon form, not just row echelon form, but reduced row echelon form. The next move is to make the 2, 2 entry become a 1. What would I multiply row 2 by to achieve that? Multiply row 2 by 2, and that will form a new equivalent row 2. So I'm going to multiply every entry in row 2 by 1/2. And that's going to form a new row 2. 1/2 times 0 is 0. 1/2 times 2 is 1. 1/2 times 10 is 5. There's my new equivalent row 2. Let's pencil that in and update our matrix. Notice I did not change row 1 this time. I just changed row 2. So row 2 now takes on the form of 0, 1, 5. And now, ladies and gentlemen, we have one extra move now. See, this is called row echelon form, but we don't want to stop here because we're trying to solve this using Gauss-Jordan elimination, not Gaussian elimination. If this was Gaussian elimination, we would stop here. This is row echelon form. But we have to go one step further to get this into reduced row echelon form. I now need to make use of row 1. I need to use row 2 to clear out the rest of column 1 above the main diagonal. In other words, I have to make this 1, 2 entry become a 0. And then we'll have reduced row echelon form. What do I add to -3 to make it 0? You have to add a +3. So what I'm going to do is I'm going to multiply row 2 by 3, add it to row 1 to form a new row 1. That's a valid elementary row operation. So I'm going to take 3 times row 2, add that to row 1, form a new row 1. Okay. 3 times 0 is 0. 0 plus 1 keeps the 1, 1 entry as a 1. Very important. It stays as a 1. Otherwise, we'll have destroyed everything we worked for up to this point. 3 times 1 is 3. 3 plus a -3 is 0. 3 times 5 is going to be 15. 15 plus a -16 is a -1. There's your new equivalent row 1. Let's pencil that in. Row 2 goes in unaltered. Ladies and gentlemen, what form is this matrix in? This is now in not row echelon form. It's in reduced row echelon form. And now that we've done all that hard work to get this in reduced row echelon form, we can just read off the coordinates of our ordered pair solution. It's that simple. Because the first row generates what equation? 1x plus 0y equals -1. In other words, 1x equals -1, x equals -1. The second equation generates the second row generates the equation 0x plus 1y equals 5. In other words, y equals 5. Done. There's your ordered pair solution. -1, 5. That's called Gauss-Jordan elimination. See how we have to go one extra step to go from row echelon form to reduced row echelon form. I know there's a little extra work involved, but you got to admit the payoff is handsome once you get your matrix into reduced row echelon form. You don't have to use any back substituting like you do with Gaussian elimination to recover your coordinates. Here, you just read off your coordinates and you're done. You just read them right off. Does that make any sense there? Gauss-Jordan elimination for solving a system of two linear equations and two unknowns there. That make any sense at all, on what just happened there? Okay. All right. Time check. 3:28. Okay. Well, let's see here. Classwork number 1, ladies and gentlemen. I want you to try one now. Classwork number 1, today is the 16th day of November. I want you to solve by Gaussian elimination. That's what the instructions would say, like on a future assessment. Solve by Gaussian elimination. So what form are we shooting for our matrix? Row echelon form or reduced row echelon form? What form are we shooting for?
Row echelon.
Yeah, all you got to do is get your matrix down into row echelon form and then back substitute to recover your ordered pair solutions coordinates. I want you to try to solve this system using Gaussian elimination. You go ahead and do this. Just follow along with the example I showed you, okay? And make sure you got that roadmap as to, you got to make the 1 entry become a 1, and then step 2, then step 3, step 4. All right, go ahead. Solve this system using Gaussian elimination, and we'll check your answer, okay? I'll give you some time to play around with that, see if you can get that done. Now, oftentimes when you solve these systems using Gaussian or Gauss-Jordan elimination, fractions do emerge. And so my word of advice is don't change your fractions into decimals. Leave them as fractions. You think fractions are messy, you ought to try decimals. So don't turn them ever into decimals. You can reduce the fractions, but always leave them as fractions. Okay. And ladies and gentlemen, since we can use a calculator, you might want to use your calculator to take care of your fractional operations. If you're struggling with those, or if you don't want to, tie up a lot of time in dealing with those, use your calculator. And if you hit your math button, just use the frac function to turn any decimals back into an equivalent fraction. Okay, so just use the calculator to take care of the basic math drudgery. All right, so I finally got my matrix down in a row echelon form right here. And now we're ready to, crank out our coordinates of our solution. So the second row would give me the equation y equals 7. That's your y coordinate of your word-pair solution. And the first row gives us a nasty equation, but it would be 1x minus 7 halves y equal to negative 41 halves. I'm going to write that equation down here. X minus 7 halves y equals negative 41 halves. 41 halves. Okay. I would multiply both sides of the equation to clear out the fractions. So you multiply everything by 2. And you'd have 2x minus 7y is equal to negative 41. Now let y be 7. Let's back substitute 7 in for y here. And now we can solve for x. So we'd have 2x minus 7 times 7 equals negative 41. Hence, we have 2x minus 49 is equal to negative 41. Add 49 to both sides. You get 2x equals 8. Divide by 2, and x is equal to 4. So there's your x coordinate. Did anybody get the ordered pair 4, 7? When all is said and done.
It took some readjustment, but I got it.
Okay. All right. Yeah. 4, 7 should be the solution of that system of two linear equations, two unknowns, and that's illustrating what's called Gaussian elimination, that entire procedure here. Okay, so 4, 7 is it. There it is in its entirety. Let's see if we can barely get it in its entirety. No, you're not going to be able to get it all in one sheet, but there it all is in its entirety. And again, use your calculator to, take the bite out of the fractional operations. I don't mind if you do that. That really is relegated for basic math. This is beyond basic math. So, I mean, if you want to do that manually to keep your mind sharp, by all means, go for it. But you don't have to. You can use your calculator to take the sting out of some of the fractions. Okay. All right. That's Gaussian elimination for solving a system with two equations and two unknowns. Ladies and gentlemen, I would like to solve a larger system now. I would like to walk ourselves through solving a system of 3 linear equations and 3 unknowns using Gaussian elimination. Notice I said Gaussian elimination, not Gauss-Jordan elimination, because that is much more involved as we got to get our matrix down into reduced row echelon form. I'll show you how to do that in a moment on a calculator on our TI-84. So just get your machine ready. But I'm going to walk ourselves through this one here. Basically, it's all the same steps of solving a system of 2 equations, 2 unknowns. It's just that we have one more step, a couple more steps thrown in because we have a larger system. But it works essentially in the same way. We pursue the steps in essentially the same manner. So I'm going to try to solve this system of 3 linear equations and 3 unknowns by using Gaussian elimination. And again, the reason why I need to expose you to this is because, ladies and gentlemen, this is on the STEM track, this class at Mott Community College, and it's presupposing that some people may actually get into computer programming down the road. And computer programmers have to understand the dynamics behind the scenes as to how things are actually performed to enable things to happen. As a computer programmer, you have to know the underpinnings of everything, okay, in order to convey it to a machine. Once you type it in as a computer program to the machine, the computer, then the computer can use its tremendous speed to solve these systems within a blink of an eye, okay? But it still requires a programmer to know that. And if we all became button pushers in society, ladies and gentlemen, that would be great. But the problem is if we were all button pushers and nobody knew anything about the underpinnings or the mathematics behind the scenes, we would never be able to advance society to the next level. We would be stuck in a rut, just pushing buttons for the rest of our existence. So because we show you the mathematics behind the scenes, somebody might actually be able to extrapolate this knowledge into new territories that are uncharted and be able to further advance our technological society. So that's the reason why we show you the mathematics behind the scenes, because there might be somebody out there that might be able to extend this knowledge and extrapolate it into new ideas. Okay. All right. This is equation 1, 2, and 3. To express this now, ladies and gentlemen, as a matrix, we're going to express it as a 3 by 4 augmented matrix. The first equation goes in as such. Second equation goes in as such. Third equation drops in as such. And now it's our job to reduce this down to row echelon form by performing elementary row operations. First of all, I have to make the 1 entry become a 1. To do that, we can either interchange rows 1 and 2 or rows 1 and 3. Doesn't matter, take your pick. I'm going to interchange rows 1 and 2. You gotta love this elementary row operation. It's a very easy one to implement. All you do is just swap rows. This is the funnest elementary row operation right here, this one. Okay. Just kind of keep track of my work and let me know if I made any obvious mistakes. All right. As humans, we are prone to mistakes. So just, you know, just kind of maybe double check things one last time before you move ahead. Looks good. Okay. Now we got a 1 in the 1-1 position. We have to use row 1 to clear out the rest of column 1. I have to make the 2-1 entry become a 0 and the 3-1 entry become a 0. How do I accomplish all that? Well, to make the 2-1 entry become a 0, I have to add a -2 to it. Where am I going to get that from? I'm going to multiply row 1 by -2, add it to row 2 to form a new row 2. And ladies and gentlemen, I'm also going to make this 3-1 entry become a 0. I have to add a -1 to it. Where am I going to get it from? I'm going to multiply row 1 by -1, add it to row 3 to form a new row 3. So I'm going to undertake all these elementary row operations to clear out the rest of column 1. Make this a 0 and make this become a 0. All right, let's see if we can do that. I'm going to do this one up here first. So -2 times row 1. And then to that, I'm going to add row 2. To form a new row 2. So here we go. -2 times 1 is -2 plus 2 is 0. -2 times -2 is 4. 4 plus a -8 is a -4. Concentrate. Don't go too fast. You make a mistake. One mistake, the whole thing's toast. -2 times 14 is -28. -28 added to 54. Uh-oh, what's 54 minus 28? That's 26. -2 way over here times a -1 is a +2. +2 plus a -4 is a -2. There's your new equivalent row 2. Let's pencil row 2 in. Notice I'm not, what row am I not changing here? What row is not being changed?
1.
1. We're using 1 to clear out the rest of column 1. We're not changing row 1. Okay, so my new row 2 becomes this guy right here. Now I'm going to transform row 3 by adding to row 3 -1 times row 1. So -1 times row 1. And then to that, we're going to add row 3 to form a new equivalent row 3. So -1 times 1 is -1. -1 plus 1 makes the 3-1 entry become a 0. -1 times -2 is 2. 2 plus a -3 is a -1. The 2 entry becomes -1. -1 times 14 is -14 plus 19 is going to be what? 5. That's the 3-3 entry. And then -1 times -1 is 1. 1 plus a -3 is a -2. So the 3-4 entry becomes a -2. That's your new equivalent row 3. Let's pencil it in. Our matrix has now been updated and transformed to an equivalent matrix looking like this. Now, ladies and gentlemen, the next move is we have to make the 2-2 entry become a 1. To do that, we multiply row 2 by, don't add anything to row 2. If you add anything to row 2, a multiple of another row to row 2, you're going to destroy this. You're going to turn this into something that's not 0. We want to keep this as 0. So we just multiply row 2 by -1/4 to make the 2-2 entry become a 1. So I'm going to take row 2, multiply it by -1/4 to form a new row 2. That's to say I'm taking -1/4 times my row 2, which is this right here. Here we go to form a new row 2. -1/4 times 0 is 0. -1/4 times a reciprocal -4/1 is 1. -1/4 times 26, unfortunately, is a fraction. -26, it's going to be -26/4. But what does -26/4 reduce down to? -13 halves. Always try to reduce your fractions. Negative 1/4 times negative 2 is going to be a positive 2/4, but a positive 2/4 is 1/2. There's your new equivalent, row 2. Let's pencil that in. New row 2 goes in like this. Again, don't turn fractions into decimals. Leave them as fractions. You can reduce them, but always leave them as fractions. All right, now, ladies and gentlemen, that we got our matrix looking like this, we have to use row 2 to clear out the rest of column 2 below the main diagonal. So I have to make this 3-2 entry become a 0. What do I add to it? Positive 1. Where do I get the 1? I get the 1 from row 2. So all we got to do now is take row 2, add it to row 3 to form a new row 3. Row 2 plus row 3 to form new row 3. And I don't really have to go off the side of my paper to do this. We can do this visually right from looking at the matrix here. Notice I'm not changing row 2. I'm using row 2 to clear out the rest of column 2 below the main diagonal. All right, so here we go. I'm going to add row 1 to row 2 to form an, I'm sorry, row 2 to row 3 to form a new row 3. So what's 0 plus 0? Keeps the 3-1 entry as a 0, and that's critical that remain a 0. 1 plus a negative 1 makes the 3-2 entry become a 0. Negative 13 halves added to 5. Uh-oh, what's that? Well, that's negative 13 halves added to 10 halves. 10 halves, another name for 5, would give me negative 3 halves. That turns this into negative 3 halves right here. 1/2 added to negative 2 is going to be negative 4 halves plus 1/2. Negative 4 halves, another name for negative 2, would give me negative 3 halves. All right, one last move, ladies and gentlemen, is to make the 3-3 entry become a 1. So what do I have to multiply row 3 by to make this 1? I'm going to multiply row 3 by negative 2/3 to form a new row 3. So I just multiply all these entries in row 3 by negative 2/3. All right. Now I got to continue another piece of paper here. So when we do that, what matrix ensues? So we got 1, negative 2, 14, negative 1. Row 2 is 0, 1, negative 13 halves, 1/2. Now here comes our new equivalent, row 3. You know, another thing you could do, instead of dragging this off to the side, down below your paper, whatever, you can just put a little negative 2/3 out here. And now it's going to negative 2/3 times all these entries. Okay, think of it that way. So negative 2/3 times 0 keeps the 3-1 entry as a 0. Negative 2/3 times a 3-2 entry of 0 keeps the 3-2 entry as a 0. Negative 2/3 times negative 3 halves makes the 3-3 entry become a 1. That's what we want. Negative 2/3 times a negative 2/3. Negative 2/3 times negative 3 halves, rather, makes the 3-4 entry become a 1. Ladies and gentlemen, what form is this? This is called, finally, row echelon form. From the bottom row, we can recover what equation? Remember, this is the x column, the y column, the z column. So from the bottom row, we get 0x plus 0y plus z equals 1. So z is equal to 1. The second row generates what equation? 0x plus 1y. So we got 1y minus 13 halves z equals 1/2. The first row generates the equation 1x minus 2y plus 14 equals negative 1. Now to recover our ordered triple solution, we just have to back substitute. Knowing z is 1, I back substituted up into the second equation. Now I can solve for y. Hence, my equation becomes y minus 13 halves times 1 equals 1/2. To solve for y, I add 13 halves to both sides. Y is equal to 13 halves plus 1/2, which means y is 14 halves, which means y is 7. Ladies and gentlemen, now we know y is equal to 7. So we know z is 1, y is 7. Back substituting those values up into the first equation, we can then solve for x. So in for z, wait a minute here. This should be 14z here. There should be a z next to 14 here, equals -1. So in for z goes 1, in for y goes 7, and we solve for x. So therefore we'll have x minus 2 times y being 7, plus 14 times z taking on the value of 1, equals -1. Now we just solve for x. So we got x minus 14 plus 14 equals -1. These drop, and x is equal to -1. We're finally done. So our ordered triple solution to this system of 3 linear equations and 3 unknowns, the x coordinate is -1, the y coordinate is 7, the z coordinate is 1. Ladies and gentlemen, that is your ordered triple solution to this system of 3 linear equations and 3 unknowns. Okay, that's called Gaussian elimination to get there. All right, you can see it's quite a procedure. Now, I know there was at least one student on planet Earth, ladies and gentlemen, that's seen this technique, that learned the math behind the scenes, and that was able to program computers and calculators to solve these systems within a fraction of 1 second. So now I'm going to show us how to solve this system over again, but by using our TI-84 calculator and using a very powerful function called the RREF function, which stands for, what do you think RREF stands for? RREF, reduced row echelon form. So now I want to show you using our calculator how we can do this. So let's go get our calculator, and we're going to solve this system now using our TI-84 calculator. All right. First thing we got to do is we got to type in this system in the form of a 3x4 augmented matrix. In other words, we got to type the system in so it looks like this into our calculator. So how do we do that? Well, we go to our calculator. We have to go into what's called the matrix mode. Matrix, notice, is above the x to the -1 power button, or sometimes it's called your reciprocal button. To get it to matrix mode, we hit our second key followed by the x to the -1 power button. We go over to edit, hit enter, and now we have to type in 3 rows by 4 columns. We need to enter in a 3x4 matrix. Ladies and gentlemen, we now type in the numbers that you see in the matrix that we laid out on our paper. We got to type all these numbers in, type the system in. Make sure you type it in correctly. Garbage in equals garbage out when it comes to computers. They're just doing what you tell it to do. Okay. Uh-oh, wait a minute here. What just happened here? Okay. 2, -8. Like I said, don't type this in too fast. You're going to make data entry errors, and once you do, your solution is toast. So I'm typing this system in as a 3x4 augmented matrix. All right, there we go. We've typed in this system of 3 linear equations, 3 unknowns as a 3x4 augmented matrix. Ladies and gentlemen, we are ready to see some magic here now. All right, so we're going to solve this system using our calculator. So the next move is, once we type our system in the form of matrix, we have to get out of this mode by hitting second mode to quit. Second mode quits. Now we got to go back to matrix mode, second reciprocal, X reciprocal button, go over to math. Notice matrix name A contains our system. Go over to math and then scroll down. Keep scrolling down till you run into a very powerful little function called the RREF function. That stands for, what do you think it stands for? What does that stand for? Reduced row echelon form. Hit enter. Now we got to go back to matrix, second reciprocal button, but stay on names this time and select matrix name A. Closed parenthesis. Are you ready for this? Hit your enter button and watch how fast your calculator can solve this system. Boom, done. In fact, it actually solved it quicker than what we've seen it. It's just that it takes time to present it to the screen. Internally, it had this thing solved within a fraction of 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 a second. Ladies and gentlemen, your ordered triple solution is x equals -1, y equals 7, z equals 1. Done. Notice our matrix is in reduced row echelon form. You gotta love that function, and it would become even more apparent how powerful that function is if you're to solve a system of 20 linear equations in 20 unknowns. To do that manually by hand would take an eternity, not to mention all of the mistakes that would occur along the way. And so, ladies and gentlemen, like I said, computers got us beat in two departments: perfect recall and speed. Humans cannot compare to those two things when it comes to computers. However, computers are very stupid devices. In fact, they don't even know what to do. They don't know what to do until told what to do. And who tells them what to do is somebody called a computer programmer. And they drag computer programmers through a lot of math to get a degree in software engineering, because they want them to be able to see the underpinnings of the mathematical world so that they can implement it in the form of a program to program machines or to create apps. All right. And that's why it's wonderful to see the math behind the scenes so that you can really appreciate what it is you're trying to have the machine do. If we are all button pushers, ladies and gentlemen, there's no way that we're going to be able to program computers with new programs or new ideas, because we're just used to pushing buttons. We don't have a clue of the mathematical background as to why things work the way they work. Okay. All right. Does this make sense here? The RREF function can save a lot of time, correct? All right. All right, the time is now 4:02. Ladies and gentlemen, I need to show you a couple of cases. So far, all of our systems have had one solution, one ordered pair solution or one ordered triple solution. All right. Do you think these systems are always going to have one solution? No. We've discovered in the past that systems of two linear equations or two unknowns, or three linear equations, three unknowns, can either have one solution, no solutions, or infinite number of solutions. We need to look at a situation where a system of linear equations has maybe more than one solution. So I'm going to show us that right now. I'm going to have us solving this system of three linear equations and three unknowns using our TI-84 calculator and the RREF function. So I want you all to, first of all, write this system down or take a picture of it, and then we're going to go to our calculator, okay? Go ahead. I'll give you about 1 minute to write that system down. Go ahead. All right, let's take it to the calculator now. All right. Okay, so here we go. We go to matrix, edit. 3x4 matrix needs to be entered in, 3 rows by 4 columns. And now we're going to type in the system I wanted you to write down. So we got 1, -4, 7, 14, -2, 9, -16, -31, 1, -7, 13, and 23. Okay. All right, now we're going to have the calculator solve this system using the RREF function. So to do that, we get out of this mode by hitting second mode to quit. Go back to matrix, go over to math, go down and grab the RREF function. There it is. Got to go back to matrix, stay on names, select matrix name A, hit enter, sit back and relax. Boom, done. Now, what are we looking at though? What are we looking at? There's the solution, all right? The system's been solved. Notice my matrix is in, technically it's in reduced row. Well, you know what? It's not in reduced row echelon form, but it is at least in what? Row echelon form. Do you agree? It's in row echelon form, all right? Ladies and gentlemen, how do we interpret what that matrix is saying there? Well, I'm going to show you. This is what it's saying. There's our matrix. The bottom row is saying that we really have the equation of 0x plus 0y plus 0z is equal to 0. In other words, 0 is equal to 0, which is a true statement. So this system of equations has an infinite number of solutions, infinite number, because this is a true statement down here. The second row is giving us the equation 1y minus 2z equals -3. The first row gives us the equation 1x minus 1z is equal to 2. Now, here's what we do. To represent what all infinite ordered triple solutions to this system look like, what we're going to do, ladies and gentlemen, is we're going to choose the z variable to be a free variable, meaning that it can be free to take on any numeric value. But then we're going to solve equations 2 and 3 for x and y, or y and x respectively, in terms of z. So in other words, if I take equation 1 here and solve it for x in terms of z, I would have to add z to both sides, and I get x is equal to 2 plus z. If I solve my second equation for y in terms of z by adding 2z to both sides, I get this. Therefore, this is a very accurate way of representing what all ordered triple solutions to this system of 3 linear equations, 3 unknowns would look like. It's got to be the set. We use set notation, use the open brace. The set of all ordered triples where the x coordinate must be 2 plus z, x coordinate must be 2 plus z, the y coordinate must be 2z minus 3, and the z coordinate is free to be anything, such that z can be any real number. So, ladies and gentlemen, you can see why this system has an infinite number of ordered triple solutions, because z has an infinite number of choices. We can assign z an infinite number of real number values. Whatever the z coordinate is, the y coordinate has to be this, and the x coordinate has to be this. That's your solution set. Any questions? How we represent it, or how we solve that system, which is called the dependent system, and how we represented a solution set as such. Okay, that's called a dependent system. There's an infinite number of ordered triple solutions. All righty. Now, ladies and gentlemen, I want you to all solve this system using your calculator. Use your TI-84 calculator and the RREF function. Go ahead and solve this system. Oh, wait a minute. What would go in for the 3-1 entry for the x coefficient for the third equation? What am I going to put in for the x coefficient for the third equation here? 0, because there is no X. Go ahead, type that in your calculator and solve that using RREF. I'll give you a couple minutes to do that. We can call this classwork number, I don't know, 3 or so. All right. And then we'll come back and look at the results and interpret the results. All right, so when you solve that system using the RREF function on the TI-83 or a TI-84 calculator, your resultant matrix is going to look like this. Everybody see that? Now, from the bottom row, we would get what equation? We would get 0x plus 0y plus 0z equals 56. In other words, 0 equals 56. 0 equals 56 is a false statement. Because of that, ladies and gentlemen, we would say that this system has no solution. There would be no solution to this system. It is an inconsistent system. Did anybody get that? Can anybody confirm my result?
I got something different. I think I put it in correctly.
Yeah, me too.
But did you get the same conclusion though at the bottom?
It gets no solution, but it's 0001 for
Okay,
me.
0001.
Yeah.
Here. All right. Okay, the bottom line is, maybe, I don't know, maybe I type this in wrong, but the bottom line is when you get a matrix that looks like this, when you solve a system 3 equations, 3 unknowns, using the RREF function on the calculator, you would conclude there'd be no solution to the system because 0 is equal to like 1, which is a false statement, or in my case, 0 equals 56. There would be no solution. Is that making sense there? Okay. All right, ladies and gentlemen, let's see. I think that's pretty much it. Now, I want you to, I want everybody in your spare time, hopefully you can buy some spare time somewhere in your life. And I would like you to at least look over examples 4, 5, and 6. And those examples are in section 6.1. So just make a note. I do want you to at least look down through these examples, 4, 5, and 6. I think one of the examples shows you a wonderful application of systems of equations. Let me quickly go look in the textbook and make sure that those are all in 6.1. I believe they are. I think I have an ounce of time left here. Let's see here. Example 4. Yeah, I want you to look at example 4 here. Just kind of walk down through the steps your author's laying out here. Example 5. Notice this is wonderful here because your author shows you all the steps that are involved to solve a system of 3 equations, 3 unknowns using the Gauss-Jordan elimination. I just use Gauss elimination, but this takes it all the way down to reduced row echelon form. Notice all the way down here. And then you can read off your ordered triple solution. Look that example over. Your author does a good job, and you will really gain a lot of knowledge just by going through the steps, okay? And also example 6. Wait a minute, where is example 6? Is there an example 6 in here? Why did I say example 6? You know, that might be in the next section. Let me look at 6.2. Hold on one second here. Oh yeah, okay, hold on. I gotta log in again, timed me out. I think that might be in section 6.2. All right, let me just quickly look here. I believe it's in section 6.2. Okay. All right, section 6.2. Section 6.2 is entitled Inconsistent System and Dependent Systems, and I've shown you what the matrices have to look like to determine each type. By all means, ladies and gentlemen, look through all the examples in these sections. Here's an inconsistent what system. Do you see at the bottom where we get a false statement down there? The system would have no solution. Here's an example of a a dependent system where we get a true statement at the bottom, 0 equals 0. So this system would have 2 solutions. And notice how they represent all the ordered pair solutions. Notice this. They let x be the free variable to take on any real number, and then they solved this equation, the second equation here, for y in terms of x to represent all ordered pair, infinite ordered pair solutions and what they would look like. So, you know, look over these examples here. There's another beautiful example. I would recommend you look at all these examples. I mean, it doesn't take that long just to look through the examples. I mean, you don't have to work through the problems if you don't want to, but at least look at the examples. There's a wealth of information you can gain by just, you know, looking through the steps. Okay. Oh, this is a good application problem. It involves traffic flow through 4 different intersections, A, B, C, and D. Just remember, ladies and gentlemen, that traffic entering into an intersection has to be equal to traffic exiting out of an intersection. That's the key assumption here. They come up with a wonderful system of equations here to model the traffic flow on this busy intersections here. And then they solve the system using the RREF function on the calculator. You know what? They actually show you the steps manually, how to transform this system of 4 linear equations and 4 unknowns into a solution. And they end up with what? A solution down here where we get an infinite number of solutions in reality, but they let x sub 4 take on any numeric value between 250 and 300. And therefore, you can deduce what the traffic flow rates would be through the other 3 intersections x sub 1, x sub 2, and x sub 3. That's a wonderful example to illustrate the application of matrices to real world problems here, okay, to try to model traffic flow, okay, and to determine some useful information. Why matrices? Because again, computers are ideally suited for working with matrices. They're called arrays, ladies and gentlemen, like a 3 by 4 matrix, what we're calling a matrix. in computer science would be called a 3x4 array. All right. And that's why it's worthwhile to be exposed to this, especially if you're going into computer programming. You have to start understanding what matrices are and how to manipulate matrices, so as to teach a computer how to manipulate them. And then once you do all the hard work of teaching a computer how to manipulate them, you can sit back and let the machine do its work within a fraction of a second. Okay. All right. So that's going to do it, ladies and gentlemen. I hope you have a great weekend. I will update the homework. And I also have to get the latest exam posted on Canvas. So I have a lot of work to do with this class, coupled with all my other duties. I am up to my neck in work. Okay, but I will update everything and get it updated for you. And hopefully we can wrap this up next week. Now, I am supposed to hold class on Wednesday, the 23rd of November. I know that's in lieu of the Thanksgiving Day. Some of you may have to, travel or whatever, but I will make the recording available. But I still have to hold class on Wednesday, the 23rd. Okay. All right. You have a good day. I'll hang on the line for a couple minutes if you have any questions.